All right, section 8.4 is a reaction with an alcohol. It actually forms an alkene. It's an elimination reaction. In fact, the mechanism is very similar to an E1 mechanism. I call it E1-like. You don't use an alkyl halide, you actually use an alcohol. So just to kind of show you a general reaction, if you have an alcohol, if you add acid and heat, remember in the E1 chapter we learned, E1, E2 chapter, if you add heat, you get an elimination. Okay, but so adding heat favors elimination reactions. So with the acid, remember, anytime you have an acid, you always have water in there. That's going to be important when we look at the mechanism. And what happens is you can eliminate water. You form a double bond, plus you form water as a byproduct, and this also follows Zaitsev's rule. Okay, so we learn Zaitsev's rule, which was the more substitute a double bond is going to form. Okay, so let's look at the mechanism of this reaction. And like I said, it's E1-like, meaning you're going to form a leaving group, it's going to turn into a carbocation, and then you're going to pluck off a hydrogen to form your double bond. So when you add acid, your oxygen is acting as the Lewis base, because that's the most negative thing. Your acid's the most positive thing, and plucks off a hydrogen. And water, when it's attached to a carbon with a plus charge, is a very good leaving group. Okay, notice we have a water molecule here. You have H2O, you have two hydrogens and oxygen. Basically, it's water attached to a carbon. It's a very good leaving group because your oxygen is relatively electronegative and it does not want to have a positive charge. So it's going to break the bond, and it's okay breaking a carbon-oxygen bond. The reason is because you form a carbocation. And the more stable the carbocation, the more likely it's going to leave. So in this case, we're forming a tertiary carbocation, so that's very stable. Okay, so tertiary carbocation. Sorry if that ran off the page, but basically that says tertiary carbocation. Okay, so you can see how this is kind of E1-like already. You have a leaving group, you have a carbocation. Now remember, your hydrogen next door to the carbocation is what gets plucked off in the elimination. So water now comes by, acts as your base, plucks off the hydrogen, and the electrons between the carbon and hydrogen now stabilize that carbocation and form the pi bond. Okay. Notice your acid is a catalyst. Notice we consume 1 mole of it and we regenerate another mole. Technically, a H3O plus is being spit out of the reaction. Okay, so this is a dehydration reaction. Okay, the next reaction they talk about in this chapter is an oxidation of alcohols. All right, we talked about reduction in the last section. Reduction was you go from more bonds to oxygen to less bonds to oxygen. Here, an oxidation in alcohols means you are increasing your number of bonds to oxygen. So you're going the other way. Okay. Here's kind of a easy thing to kind of see. Let's say you've got an alcohol. So this is kind of off the topic a little bit. I mean, it is and it isn't. If you do if you oxidize this by 1 degree, you get a double bond to oxygen. Okay, so here you have 1 bond on the alcohol, you have 1 bond to oxygen. Here you have 2 bonds to oxygen. So this is an aldehyde. If you oxidize it another step, you now should have 3 bonds to oxygen, and that's a carboxylic acid. So now you have 3 bonds to oxygen. So notice as I'm increasing the number of bonds to oxygen, I'm technically oxidizing it. The reverse is reduction. So if I go from 3 bonds to oxygen and I reduce it, remember adding hydrogen, you now go to 2 bonds to oxygen. And then reduce it 1 more step and you go to an alcohol. So this is kind of a good thing to actually understand and know. It's the, I guess it's kind of a little chart to show you how oxidation and reduction occurs. Alcohol is the least oxidized. Carboxylic acid is the most oxidized. Okay, so let's go on to oxidation. So how do you oxidize? There are going to be 2 reagents that we're going to use. All right, so there are 4 oxidizing agents that we're going to look at. We're not really going to look at the structures of them per se. One is called PCC. Okay, it stands for pyridinium chlorochromate. You don't need to know that. But it's basically an oxidized form of chromium. Chromium has been found to be a very good oxidizing agent to organic molecules. Another really strong oxidizing agent is sodium dichromate in acid. So this is always in acid. And another one is CrO3 in acid. They kind of do the same thing. Notice these are chromium compounds. Remember, PCC is a chromium compound. These are great oxidizing agents, but they have chromium. And chromium is not that good for the environment or for us. It's very toxic. So there's a new oxidizing agent. It's not new, but it's new in kind of books because it's been shown to work really well, is a periodinane. It's a very highly oxidized iodine. Okay. The iodine is very oxidized. It has a lot of oxygens attached to it, and then it can oxidize organic molecules. The only problem is it is kind of expensive. You can't really use it on very large scale. So if you're like a big pharmaceutical company and you need to do an oxidation, periodinane is not the best choice. But for small scale, and nowadays it's so commonly used. We're going to so instead of using PCC, you can use the periodinane instead. So these kind of are interchangeable. So I'm going to kind of use both. I'm going to kind of use PCC because that's more what's been used. But just note that your book does use more of the highly oxidized iodine compound. So you'll see them both, but these can be used interchangeably. Okay, so let me show you when you use each one and why you would use each one. Okay, so the PCC is used in one case, and these two can be used in a different case, and they kind of do the same thing. Periodinane is very similar to PCC. So what you can do with the periodinane, you can do with PCC. What you can do with PCC, you can do with the periodinane. Okay, so first let's talk about primary alcohols. What can you do with primary alcohols? Well, if you have a primary alcohol, you can oxidize it to an aldehyde. You can also then further oxidize it to a carboxylic acid. Okay, let's look at a secondary alcohol. What can you do with a secondary alcohol? Well, a secondary alcohol, the only thing you can do is oxidize it to the ketone. All right, it does not oxidize to the carboxylic acid because you have two carbons on each side. So depending on the type of alcohol you have, you can either completely oxidize a secondary to the ketone, or you can take a primary, oxidize it to an aldehyde, or even oxidize it even further and go to the carboxylic acid. Okay? So let's first talk about the primaries. Okay? To stop at the aldehyde, if you want to stop the oxidation at the aldehyde, let's say you want the aldehyde compound, okay, you either use the PCC or the periodinane. These are not that strong of an oxidizing agent. They're strong enough to stop it at the aldehyde. Okay? So for primary alcohols, PCC or periodinane, I don't care which one, I will use both of them. Your book kind of uses the periodinane more than the PCC. In fact, I don't even think they talk about PCC anymore in there. But I just want to make you aware of it because that's what I'll probably be using more often. All right, so that stops at the aldehyde. Let's say you have the same alcohol and you want to go to the carboxylic acid. You don't want to stop at the aldehyde. You want to synthesize the carboxylic acid. Well, this is where you use the chromium salts. So you either use the sodium dichromate, this is called sodium dichromate in acid, or you can use the chromium 3, actually it's chromium 6, but it's CrO3 in acid. So that is a very strong oxidizing agent that can completely oxidize it to the carboxylic acid. It does not stop at the aldehyde. It goes completely to the carboxylic acid. Okay? So PCC or periodinane to get the aldehyde, stops at the aldehyde. Sodium chromate or the CrO3 in acid, sodium dichromate or the CrO3 to go all the way to the carboxylic acid. It doesn't stop at aldehyde. Okay? It goes all the way to the carboxylic acid. Okay? Now, for secondaries, it doesn't matter which one you use. It's going to do the same thing. So if you have a secondary alcohol, remember, you can only oxidize it up to the ketone. So you can use any of the four reagents, PCC or periodinane, I'll put period, or you can use sodium dichromate, or you can use CrO3 in acid. Okay, so for the secondaries, you can use any one because it stops. You can't go any further. But for the primaries, you can go to an aldehyde. So PCC and pariadenane are the choice, either one. If you want to go to the carboxylic acid, use the sodium dichromate or the chromic acid. Okay? So let me kind of show you a little chart that I'd like to do. So this kind of chart is going to summarize oxidation and reduction all in one step. So if you want to go to an alcohol to an aldehyde, you either use PCC or pariadenane. All right. If you want to go from the alcohol to a carboxylic acid, you add Na2Cr2O7 in acid, or you can add CrO3 in acid. Okay? If you want to go from the aldehyde to the carboxylic acid, same thing. These reagents will do the same thing. Okay? So if you have an aldehyde and you want to go to a carboxylic acid, add Na2Cr2O7. Sorry, that should be a 7. That should be a 2. Sorry about all that. Or CrO3 in acid. Okay, so this is a little chart. To go from alcohol to the aldehyde, you use PCC or the pariadenane. If you want to go all the way to the carboxylic acid, use the Na2Cr2O7 in acid. Okay, that's basically what we learned. Now let's talk about the reduction part of it. So the bottom is going to be the reduction. All right, if you want to go from an aldehyde to an alcohol, what reagent do you add there? That was in section 8.3. You can either add sodium borohydride, remember that's a mild reducing agent, or you can add LAH. Okay, that's the stronger one. Okay, if you want to go from the carboxylic acid to the alcohol, just LAH. Remember, sodium borohydride won't do it. There is no way to go from the carboxylic acid to the aldehyde. They're much more exotic and complicated and very expensive reducing agents. They also only work if things are very dry and you don't have any oxygen and the moon has to be in a certain phase. I mean, it's very complicated to do it. So what people usually do is if they want the aldehyde, starting from the carboxylic acid, so let's do a generic carboxylic acid, what they'll do is reduce it all the way down to the alcohol, and then they'll oxidize it back up with PCC or pariadenane and get the aldehyde. Okay, so they reduce all the way down and then they bring it back up to the aldehyde. All right, and then the last reaction in this section, it's kind of a big section, is called the Williamson ether synthesis. This is something that you've already learned in the SN2 chapter, but they talk about it again and they actually give a name to it to make it sound so important. The Williamson ether synthesis, it's basically an SN2 reaction. Not basically, it is an SN2 reaction. What you do is you start with an O negative, which remember we learned comes from the alcohol. You can take the alcohol and add sodium metal to form that, and add it to whatever alkyl halide you want. Let's put the chlorine. And remember, it's SN2. This attacks your carbon, your chlorine leaves. So this is something we've already learned. They just have a name to it called the Williamson ether synthesis. It's an SN2 reaction. Okay? We'll do a bunch of synthesis problems when we get together. I'll have a bunch of synthesis problems, and we'll start looking more at these oxidations and these reductions. So that's 8.4. And obviously, if you have any questions, we'll talk about it in class.